Welcome to Module 1 of the Digital Twins and Digitalization of High-Pressure Die Casting Foundries training program. In this opening module, we set the stage for everything that follows. We will explore how die casting has evolved from a well-understood high-volume process into the frontier of megacasting, where a single shot of molten aluminum can replace dozens of stamped, welded, and bolted assemblies. Understanding this shift is essential before we introduce sensors, simulation, and digital twin architectures in the modules that follow. For most of the 20th century, high-pressure die casting served the automotive industry with parts under 10 kilograms, engine blocks, gearbox housings, brackets. Locking forces of 800 to 1,600 tons were the norm. Then, over the last decade, electric vehicle architectures pushed the industry to consolidate structural components. Machines with 6,000, 9,000, and now over 16,000 tons of clamping force appeared on foundry floors. What used to be a component-scale process became a body-and-white scale process, almost overnight. Filling a small cavity is a matter of milliseconds. Filling a 2-meter structural casting is a controlled explosion. Molten aluminum must travel meters through complex runner systems at velocities exceeding 40 meters per second, without turbulence, without cold shuts, and without entrapping air. The relationship between gate velocity, cavity pressure, and solidification time no longer scales linearly. Small errors in shot profile that were invisible on a bracket become catastrophic on a rear underbody. This is why intuition and legacy process sheets are no longer sufficient. Megacastings demand new aluminum alloys, typically high ductility, low iron, secondary or primary formulations that can absorb crash energy without heat treatment. But these alloys are unforgiving. Cooling rates vary dramatically across a single part, fast at thin ribs, slow at thick bosses. The resulting microstructure, dendrite arm spacing, porosity distribution, intermetallic phases determines whether the part passes crash validation or ends up in the scrap bin. Controlling this thermal history at scale is one of the central problems digital twins are designed to solve. At megacasting scale, the die is no longer a tool, it is a structure. Blocks weigh over 100 tons. Thermal gradients across the die face create bending moments comparable to those in bridge engineering. Heat checking, soldering, and core pin deformation, which used to be maintenance nuisances, now translate directly into millions of euros of unplanned downtime. Predicting tooling behavior over hundreds of thousands of cycles is no longer optional. It is the difference between a profitable line and a stranded capital investment. Traditional foundry engineering relies on trial shots, destructive testing, and the experience of senior technicians. That model does not scale to parts that cost thousands of euros per shot and tools that take a year to build. Every cycle of a modern press already generates gigabytes of pressure, temperature, position, and vibration data. The question is no longer whether to instrument the process. The machines are already instrumented. The question is whether that data is captured, contextualized, and fed back into decisions. By the end of this module, you will be able to clearly explain the structural differences between conventional HPDC tooling and megacasting tooling, and articulate why they demand different engineering disciplines. You will be able to assess the thermal gradient challenges of massive cast parts, and reason about their impact on quality, cycle time, and cost. Most importantly, you will have the shared vocabulary needed to engage with the digital twin architectures, simulation workflows, and predictive maintenance strategies covered in modules 2 through 6. In the next module, we move from context to construction. We will define what a foundry digital twin actually is, the sensor layers, the edge and cloud infrastructure, the data models, and the feedback loops that make it a living system rather than a static three-dimensional drawing. Thank you for completing Module 1. Take a moment to reflect on your own foundry and consider which of the challenges we just discussed already keeps your team awake at night. That is where your digital transformation will pay off first.